Example 8. Using f prime of x and f double prime of x, so using the first and the second derivative to graph f of x, given the derivative. So we've explored something like this back in example 3 or 4, and we talked about how if you're given the graph of the derivative, how you graph the original function. So now we're going to do the same thing, except this time instead of be giving a graph, we're going to be given a function. So I want to start out by thinking about what does each derivative tell us. So the first derivative tells us critical points, our max and mins. It tells us where the function's increasing and where the function's decreasing. So it tells us all kinds of information about increasing and decreasing. Should we be going up? Should we be going down? That kind of things. What does the second derivative tell us? The second derivative tells us inflection points. It tells us where the graph curves up when where it curves down. This is the smiley face. Where is it bent up and where is it bent down? So I'm going to walk you through step by step how to determine how to graph this function. I break it down to, I think, 5 steps. If you can condense the steps or if you need to separate the steps, that's also fine. So step 1, we need to determine our critical points. So we need to determine our critical points. And here we go, let's do that. So f prime of x is equal to 4x cubed minus 12x squared. So to determine critical points, we set our derivative equal to 0. And I'm going to go ahead, I'm going to factor out a 4x squared. So I'm left with 4x squared and then an x minus 3. And from there, I just solve. I get 4x squared equals 0, x minus 3 equals 0, and I'm left with x is 0 and x equals 3. So those are my critical points. Alright, pretty easy. Step 2, determine the intervals of increasing and decreasing for our original function. Remember, the derivative tells us where a function is increasing and where a function is decreasing. So to do that, we're going to make a sign chart. So we make our sign chart. And we're going to place our critical values right here for 0 and right here for 3. And in order to determine increasing or decreasing, we picked x values on each side of the critical points. So -1, 1, and 4. So there's a couple ways to determine increasing or decreasing. I'm going to go ahead and just plug in the points into the derivative. If you want, you could use the second derivative test and plug these values in to see what happens. But I'm just going to go ahead and plug in the derivative. It doesn't seem that hard. F prime of -1 is 4 times -1 squared -1 minus 3. Notice I'm using the factored version because it's very easy for me to tell if you have a negative or positive sign in the factored version. For example, this is positive. This is negative, so the whole thing is negative. So it's a minus, so it's decreasing. Now I'm going to use 1. F prime of 1 is 4, 1 squared, 1 minus 3. That's positive. That's negative. So the whole thing is negative. So this is interesting. This is a case where 0 then is not a local max or a local min because it's decreasing on both sides. And then we do the final one, f of 4. You get 4 times 4 squared, 4 minus 3. Everything here is positive. So this is positive, so it shoots up. So it looks like the critical point 3 is going to be an extrema. Okay, so let's talk about that for a minute. X equals 0 is a critical point, but not an extrema. since f prime of x does not change sign from either positive to negative or negative to positive. Whereas x equals 3 is a critical point, and x equals 3 is a local min, since f prime of x is less than 0 from negative infinity to 3, and f prime of x is greater than 0 from 3 to infinity. Okay, so now right here, this is very important. I have found a local min at x equals 3. I don't know the y value, but that's okay. So let's talk about where the function's increasing and decreasing then. F of x is increasing on the interval (3 to infinity), and f of x is decreasing on the interval negative infinity to 0 and 0 to 3. Now your question might be, why can't I just write negative infinity to 3? And that's because we wanted to note that it is a critical value, so we do put that. I'm going to put as a side note right here, and you might want to write this down. Always include endpoints for increasing / decreasing. Okay. That was step 2. Now for step 3. Step 3 is pretty easy. Step 3 is to determine the inflection points. So let's go ahead and do that. Let's do it in a fun color, like, let's do this one. So if f prime of x is equal to 4x cubed minus 12x squared, to determine an inflection point, we take the second derivative, which would be 12x squared minus 24x, and set that equal to 0. You get 12x, x minus 2, so x is 0 and x is 2. Easy. Those are our inflection points. That's going to move us on to step 4, determining the concavity of this function. So to determine concavity, we do the same thing. We're going to use a sign chart. It's going to help us out a lot. Remember, a sign chart does not count as evidence on the AP test. It's a wonderful tool, but it does not count as evidence on the AP test. So here we go. We got to pick values in between -1, 1, and 3. Now we just test those values to see if we're concave up or concave down. So f double prime of -1 is 12 times -1, -1 minus 2. This is negative. This is positive. So you get, oops, this is also negative. So you get a positive. So right here, it's positive, so we are concave up. Now let's check it with 1. You get 12 times 1, 1 minus 2. This is positive. This is negative. So we have a negative. So it's concave down. Now we check our last point, which is 3. And you get 12 times 3, 3 minus 2. Well, the whole thing is positive, so we get positive. And now we're almost ready to go. We've done all the hard work. Let's just write a little explanation so we can be able to write our answers in complete sentences. So we have f of x is concave up from negative infinity to 0 and 2 to infinity. We have f of x is concave down from 0 to 2. Here's another little side note. Do not include endpoints for concavity. So for concavity, we do not include the endpoints. For increasing and decreasing, we do. Okay, so step 5 is graph. This is the best part. This is all the work you've done culminating together. So what I like to do is I like to put together what's called a summary chart. This is going to give me quick little info about the graph. Again, the chart means nothing to the AP test, but to us it's super helpful. So I need to write all my different intervals. Well, I have x is less than 0. When x is less than 0, everything stays the same. The next interval I have is between 0 and 2. Again, these are not my critical points, but it's my next interval. My next interval is going to be from 2 to 3. And my last interval is greater than 3. What I'm doing here is I'm combining my inflection points and my critical points, and I'm breaking them down accordingly. So when x is less than 0, we're decreasing and concave up. When we're between 0 and 2, you're still decreasing, but we're concave down. Between 2 and 3, we're decreasing and concave up. When you're bigger than 3, now we're increasing and concave up. So this is all going to be components that are going to help us graph right now. So here we go. I'm going to zoom out to make my graph. Zoom out a little bit more. Here we go. When I make graphs, I like to make them nice and big. There's no reason to go small with graphs. If you go small, you're going to end up pinching your graph and it's going to be very hard to read. So by making your graph large, it makes it easy to read. So I know I'm going to need the x values 1, 0, which is right here. I know I'm going to need 2, and I know I'm going to need 3. So I like to add some extras just to help me out. Okay, and here we go. First step. Because we don't actually know the position of the graph, we pick a random point. I'm going to put it right, let's say here. Preferably, you don't pick one where there's a critical point or a inflection point. You just pick a random point on the graph for any other x value. Okay. Now let's plot where I might have an inflection point, where something might change. Well, it changes at 0. So, I'm going to pick any other point. And I know that to get from 0 to 1, I have to decrease. I know I'm decreasing, so I'm going to put it up here. Then at 2, I'm still decreasing, so I'm still going down. But now I go from being concave down at 2 to concave up. So I'm just going to pick another point, maybe here. And then I'm going to cross the x-axis for no good reason other than I want to. You could stay completely above the x-axis. It doesn't matter. But here at 3, remember, I have a minimum. It goes from decreasing to increasing. So I'm going to put that right here. So from 0 to 2, I'm concave down, which makes these points kind of hard. So I'm just going to erase this point. No harm, no foul. It's okay. So I'm concave down like this. I'm decreasing and I'm bent down. When I'm smaller than 0, I'm bent up. So it's going to look like this. I'm bent up and then I bend down. And now, when I am between 2 and 3, I'm decreasing, but now I'm concave up. So this is an inflection point. So now I'm starting to bend up. So let me just erase this a little bit, make my graph a little more accurate. I'm bent up and then bent down. So I know it looks kind of like a line, but that's okay. And then I stay concave up, but now I start increasing. So this is just one possible graph. It's not perfect, but it's mine. I'm just going to make my points a little more visible. And now I'm going to identify which piece of the graph goes with which piece of the table. This piece goes with right here. This piece goes with right here. This piece goes with right here. And finally, this piece is this side right here. That's how I got all the pieces at my graph. Now I want to make one big note again. This is one possible graph. As long as your graph follows all these rules, it's okay if your graph looks different than mine.